Thank you everyone for attending today's webinar, Automation Actuators, Electrics Are Taking the Stage, brought to you by PhD Inc. and Design World Magazine. If you wish to tweet about this webinar anytime during or after, you can use the hashtag DWWebinar, that's all one word, and we will have a Q&A session after the presentations. My name is Paul Heaney, and I'm the Editorial Director for Design World, as well as the site editor for Mobile Hydraulic Tips and Pneumatic Tips, which are some great online resources that I hope you all are familiar with. A little background on me. I have a mechanical engineering degree from Georgia Tech, and I've been covering the engineering and manufacturing markets for almost 15 years now. I'm very pleased to be your moderator today. I'd like to take this opportunity to thank our presenters for being here today and also to introduce them. Cale Reese is Electromechanical Products Manager for PhD, and he's been with the company for 8 years, and he serves as an Electromechanical Products Manager. He has a bachelor's degree in Mechanical Engineering Technology and was recently featured as a contributing author in the August issue of Design World. Kerry Webster has been with PhD for 13 years and serves as a segment technical manager, focusing on the aluminum smelting, carpet, and tire industries. He has a bachelor's degree in industrial automation and is a certified fluid power pneumatic specialist. John Dent, PhD's distributor training and development manager, has been with the company for 35 years, fulfilling various product engineering and design roles. He also is a certified fluid power pneumatic specialist. And Ryan Winsman has been in the fluid power industry for 9 years, 5 of which he spent PhD as a lead quote and special product coordinator. He has a bachelor's degree in manufacturing engineering, and he is a certified fluid power pneumatic specialist and manufacturing technologist. Now let's talk a little bit about today's agenda since we have the 4 different speakers. First up is electrically powered actuators versus pneumatic, and that's presented by Cale Reese. After that, Kerry Webster will be discussing actuators and motors, sizing, selection and sizing. Third is application flexibility examples with John Dent. And lastly is specialty electrical products, which will be conducted by Ryan Winsman. And now, without further ado, we'll go on to our first presenter. I will hand the mic over to Cale, who will be focusing on electrically powered actuators versus pneumatic. All right, take it away, Cale.
Good afternoon, everyone. My name is Cale Reese, as Paul had mentioned, and I'm the Electromechanical Products Manager for PhD. Today we'll be discussing electromechanics versus pneumatics. For the purposes of this webinar, what I would like to focus on is a very popular platform of rod-style actuators. And what I want to be talking about as far as rod-style actuators in electromechanical products, I'm going to be focusing on screw-driven devices. Now, as the title there says, electromechanics versus pneumatics, I want to stress that this is not necessarily a competition between the two. I'd like to discuss the benefits and the limitations of each so you can choose the best solution for your application. For this comparison, I'd like to discuss 4 key elements: performance, control, efficiency, and level of investment. As far as performance goes, and where I'd like to start, the physical attributes of each actuator determine much of the performance of the system, but in many different ways. And I'd like to break performance down into 3 elements. First, speed, thrust, and then life. Now, as far as speed goes, in a pneumatic actuator, speed is a function of your cylinder bore and your flow rate. Generally speaking, the smaller the bore and the greater volume of air one can pump into an actuator per unit time, the faster the actuator will move. And this brings one of the core benefits of a pneumatic actuator, as they are extremely fast and extremely quick. And by fast, I mean overall velocity of the unit, and by quick, I mean its ability to accelerate very fast, very quickly. As far as the electromechanical actuator goes, speed is a function of the screw lead and the motor RPM. And by screw I mean the linear translation per rotation of the screw. So, for example, an electromechanical actuator with a lead means as the motor turns 1 revolution, the actuator will translate 1 inch of linear travel. And I like to correlate the lead or the screw of the electromechanical actuator to much like that of the transmission in a vehicle. The lead of the actuator is kind of like the gear. So a low lead actuator would be equivalent to the first gear in an automobile, whereas a high lead would be more like the fifth gear of the transmission of a vehicle. Now between speed, when looking just at speed, but it's the control of that speed is where the EM actuator really shines. But when you're just looking at overall specsmanship between the two, your pneumatic actuator is going to have a lot more speed and a much greater acceleration. As far as limitations go, the limitation of your pneumatic actuator is your end-of-stroke impact, and a little saying that we like to say in the pneumatic world is speed kills. With all that velocity and acceleration capability from the pneumatic actuator comes a large amount of kinetic energy that must be absorbed at end of impact. And pneumatics are prone to self-destruct if that impact is not controlled. For the electromechanical actuator, the limitation is travel and critical speed, or also known as screw whip. It's not necessarily apparent that the travel or the actuator stroke is the major determining factor here. The longer the stroke, the slower the maximum velocity due to that condition called screw whip or critical speed. Also, something to be aware of when shopping for an actuator, it's not uncommon for manufacturers to advertise the peak speed. So it's the fastest the actuator can possibly travel, but not necessarily what it can travel at the stroke that you require. So this, again, this is a stroke-dependent specification. This chart kind of demonstrates what I'm speaking about here. We have travel versus speed, travel along the bottom and speed up the left-hand side. As your travel increases, your electromechanical actuator will have to be slowed down. But as a pneumatic, the pneumatic device, regardless of its travel, it typically has one constant peak speed. So let's move on to thrust. In the pneumatic actuator, thrust is a function of the cylinder bore and the working pressure. A very simple equation to get your thrust from a pneumatic actuator is the pressure of your working fluid times your working area, or the bore area of the actuator, and that results in the thrust of the actuator. So typically your pounds per square inch times your square inches of area equates to your pounds of thrust, which is in pounds or newtons. Here again is one of the big benefits of the pneumatics is that they have an extreme power density. There's a lot of stored energy in that fluid, that they have a lot of thrust for no more size that the actuator is. On the electromechanical side, thrust is a function of the screw diameter and lead and the motor torque. When it comes to thrust out of electromechanical actuators, it's really a balance between the motor torque and the actuator capabilities. As far as limitations go, on your pneumatic actuator, the limitation is your line pressure or your air compressor's pressure and the seals within that unit. Pneumatic systems have their pressure limitations of generally 150 psi, and that's limited by the capability of the industrial compressor's performance. And they also have performance limitations based on the seals inside of the actuator, as far as what compound the seals are made out of and what the geometry of the seal is, whether it's an O-ring or a lip seal. On the electromechanical side of things, the limitation is the screw geometry and life. There's a trade-off between thrust and speed. And again, I'm going to go back to the correlation of the transmission in the automobile. If your low speed is your first gear in your transmission, that gear is able to create a lot of thrust but not a lot of speed. Whereas if you're on your fifth gear in your transmission, you have a lot of speed but not a lot of thrust. Your screw geometry works in a very similar way, and it's a trade-off between the two. So thrust and speed have a direct correlation, but thrust and life also have a direct correlation, and I have a graph to demonstrate that. But first, before I get to that, I want to go over the fact that, let's see, where am I at? The transmission of, pneumatic function is a function of linear travel, and the dynamic seals will usually want to wear out on a pneumatic actuator by X millions of cycles. So this is kind of a predictive amount of wear. You know when that actuator is going to need replacement. And typically that is regardless of how much thrust the pneumatic actuator is putting out. And another benefit of the pneumatics is that they're typically lubricated for life, so there's no maintenance necessary on that actuator for its duration of life. Whereas on the new electromechanical actuator, the life is a function of thrust. So I alluded to this graph here. Let's take a look at this. I have life across the bottom of the graph and thrust across on the left-hand side. As your life increases, your thrust requirements need to go down on your electromechanical actuator. So it's very important to size the actuator correctly, whereas your pneumatic actuator is going to put out the same amount of thrust regardless of the life requirement of the actuator up until it's done and ready for replacement. So the point I'm trying to make here is that if your electromechanical actuator has to work very hard and it's possibly undersized for the application, its life is going to be very short. Whereas if you oversize the actuator, your life could be longer than what you necessarily need for your application. So unlike pneumatics, it's very important to know your application and size the right electromechanical actuator. So let's move on and look at control. On a pneumatic actuator, valves are the primary means of control. And these valves can be electrically, pilot actuated, or manual operated. And valves simply direct the flow of fluid to the actuator. On the electromechanical side of things, the motion controller are the brains of the system, and they control the direction, speed, and torque of the motor driving the device. And we can't talk about control without talking about feedback. On a pneumatic actuator, individual sensors relay discrete positions to the PLC, and these sensors can be magnetic, inductive, or proximity sensors. On the electromechanical side, total closed loop control via the servo motors and sensors are what gives the feedback to the motion controller, and this can come in a form of an encoder or a resolver. The benefits of a closed loop control come from the interpretation of this feedback. So the constant monitoring of the electromechanical system, it's able to correct for variances in the operation, resulting in accurate and repeatable motion over its motion. So let's go on and look for the interpretation of this feedback and how it affects performance. Control on a pneumatic actuator typically is of a mechanical means, such as flow controls, cushions, impact pads, and what I don't have listed there, but I wish I would have put on this slide was shock absorbers. The flow controls control the velocity, where the cushions, the impact pads, and the shock absorbers provide limited control for deceleration at the end of travel. Oftentimes these are elements or options that can be ordered on board the cylinder itself, the actuator itself. But each one of these features can also wear over time, so it's something to be aware of. Electromechanically, the motion controller has total control of the motor RPM. So the motion controller can control the linear acceleration and the deceleration, and also the travel velocity of the actuator. And this is done with software internal to the motion controller. An example of where you could use this kind of control would be on pushing applications or variable impacts where you need different speeds going out as coming back. And again, with a closed loop system, this control is repeatable in both acceleration, deceleration, and overall velocity. Pressure regulators are the typical way you control thrust on a pneumatic actuator. These are usually inline and typically dialed in, so you have a single set of pressure over your entire line or your machine. And actuators of similar bore will produce similar thrusts. On the electromechanical side, you have total control of the motor torque via the motion controller. Variable amperage changes motor torque, and so variable thrust can be achieved through target thrusts, and target thrusts can be maintained. Again, you can use this for pressing operations or a fault condition, whereas you don't want to have so much thrust, and the motion controller could tell you that you're over thrusting and could possibly save your machine from crashes. As far as position goes, multi-position cylinders, as demonstrated in the picture there at the bottom, are usually how you do multi-positioning on pneumatics. It's done with external stopping hardware. Generally, there's anything more than a 3-position on a rod-style actuator. You can get into very long systems or very long actuators, and these can get expensive quickly. Whereas on the electromechanical side of things, the motion controller allows the actuator to be capable out of the box of virtually unlimited positional control via the constant loop feedback. Again, this is based on the capability of the motion controller hooked up to the actuator. As far as investment goes, the initial investment for pneumatics is low if you're already set up for pneumatics, meaning if you already have an air compressor and your building or your machine is set up for air distribution. So your actuators are relatively inexpensive. You have your valves and your fittings to actuate or control the actuator, and then you have your air lines. As I mentioned earlier, your air compressor and your air prep, if you're already set up for it, is just a matter of adding the actuators to the system. But if you do have to add, or you're starting from scratch, air compressors and the complete air prep can be expensive. Depending on the performance requirements of your EM device, they're typically more expensive. Your actuator, depending, if you need a lead screw actuator or a ball screw actuator, they will be a little more expensive than your pneumatic counterpart. In addition to the actuator, you have your motor and your motion controller and your I/O cables to communicate between the two. Also, you want to take into consideration there'll be a control box or a cabinet somewhere in your machine that houses all of your I/O and controllers. A difference between these two is that every electromechanical actuator will require its own dedicated axis of control. Whereas if you already have an air compressor, again, you can just put your pneumatic actuator in line and tap into that air bus and have actuation. So that's one of the things to consider as far as cost. And then another thing to consider on your electromechanical actuator would be some of the actuators require 220, 3-phase, high voltage, things of that nature, so they can't necessarily be plugged into the wall and off you go. So you may have to run some additional power for your electromechanical. As far as costs go, as I mentioned, you have the cost of the compressor itself, and air compressors are not cheap, but the air that they compress is not free. For the longest time, it was considered that compressed air was free, and that's not the case anymore. Air compressors are power-hungry and inefficient systems, and they also leak and can be very expensive over their life, because you've got the air compressor in one corner of your building, your actuators in the other, and the lines getting between the two could leak. That could be very expensive. And it's also known that your actuator, your pneumatic actuator, is going to be eating air regardless if it's even in motion. So your air compressor those lines are compressed the entire time, I guess is what I'm trying to say, regardless if the actuator is in motion. So that leakage is happening all the time. Another thing to take into consideration is your changeover costs. If you have to change over your multi-positions because you're going to set up for a different line or run a different size part, your pneumatic actuators, you'll have to shut the line down to do that, whereas your electromechanical actuators, it can be all done in software. So looking at the electromechanical side of things, you've got your initial startup costs that we covered, your actuator, your cables, your controller. But another thing to understand is that your electromechanical actuators are a little more technologically advanced and can sometimes be difficult to repair. And many of the actuators are not field repairable. You need to send them back to the manufacturer for repair. Another thing to consider is specialized personnel required by the customer or by your staff. Again, with the technology that comes along with these actuators, things to consider are the programming and the implementation of the actuator, and also the service and repair and maintenance of it once it's in the field. As far as benefits go, I spoke to this earlier. Pneumatics have an extreme high power density. You can get a lot of power of these actuators for no larger that they are, and they also exert extreme speed. But they have low overall startup costs, if you're already set up for the pneumatics. Again, they're easy to repair, and the parts that you have to repair them with are relatively inexpensive. And deliveries are typically fast for your pneumatics. As far as the electromechanical go, the closed-loop control allows for system flexibility, and that's really where they shine, is in that control of each of the performance variables that we talked about. So this can eliminate line change or downtime by having to change your line over for multiple sizes, or you can create a machine that can actually make multiple pieces or different size pieces all on the same machine. Efficiency by consuming less air, we kind of talked about, or less power. We talked about this. The air compressor is running regardless of your pneumatic actuators running or not. It's got to keep those lines pressurized, whereas your electromechanical only consumes power when it's necessary. So this can be a solution for some of the corporate green initiatives that are coming about. Electromechanical actuators have much less noise. They have low noise, so this can satisfy some OSHA requirements. And again, they're ideal for office or medical environments. And again, they've got cleanliness. Your pneumatic actuators can sometimes exhaust air from the valves or from the actuators, where your electromechanical actuators do not have that problem. So again, makes them ideal for food or medical applications. So I'd like to wrap this up with kind of a summary to remind you guys that it's important to remember that the best solution may or may not be pneumatic or electromechanical. It could be both. But the most important thing when sizing these is to know the application, know the customer's expectations to create the optimal system. Understanding the benefits and limitations of the pneumatics and electromechanics, one can choose the best actuator for the job. And to focus, and one point I want to make is to focus technology where it's appropriate. Sometimes the pneumatic actuator will do the job just fine, where sometimes you need the control, and the electromechanical actuator can really shine with its benefits. And sometimes you can use both to create an integrated solution. If you need a two-position X-axis but a multi-position Z-axis, you can put your pneumatics on your X and your electromechanics on your Z and kind of get the best of both worlds, because the ultimate goal is to get the highest amount of value for the lowest cost of ownership. Okay, so that's it for me. I'm going to turn this back over to Paul, and he'll introduce the next topic and presenter. Paul?
All right, thank you, Cale. That was a great presentation. Appreciate it. Next up, with a focus on actuators and motors, selection and sizing, is Carrie. Carrie, take it away.
All right, it's pretty common to have three different electromechanical packages. And the first package would be the integrated actuator motor control package. This is the one where you buy an all-inclusive package where it may not be a software that you're used to using. It may not be a motor you've heard of, something like that. The second type of package would be a limited, where you may get to choose from a couple different series, maybe a software package you're familiar with. The third package, this is the one we're going to stress on today, is going to be the open architecture actuator. The ability to use your own motor and controller. If you've been using brand X for, say, 15, 20 years, you know it real well. This is the one you're going to be most familiar with. So what we're going to do next is we're going to walk you through, show you how easy it is. Now, those of you that have been using pneumatic sizing for years, you may have thought, man, electromechanical sounds complicated. I don't know anything about motor and controllers. We're going to show you how simple this is. Second thing we're going to show you the sheet that you'll use to size the motor. And then the last thing is the online configurator. You know, every time you size up an actuator, you need a CAD model to drop it in and make sure everything fits up, right? So we're going to jump over to the internet. There we go. On the PhD website, we have our sizing split into two categories: pneumatic, hydraulic, obviously, and then electromechanical. Once you click on electromechanical, you get a step through, 4 different steps, but it's actually easier than that because the 4th page is actually just a summary, right? So on step number 1, we're going through a couple different questions. We're asking you, are you going to size up the cylinder? A cantilevered slide, which would look something like this, right? A saddle slide, some call it a base slide. Today we're going to size up the cylinder. And the actuator that PhD has is the ECV. the motor mounting style. This is whether, you can do fold back design. The picture doesn't show up on here, but the fold back would be reverse parallel, for some of you heard that term before. And then the QF21 is a fold back with a 2-to-1 ratio, so it gives you double the thrust for the same motor. So that would obviously reduce the amount of speed that you would get from the same motor as well. On the right-hand side, we're going to go through application inputs, and we've made this really simple. Metric or imperial inputs. Our unit travel that we're going to deal with today is 300 millimeters, which is about 12 inches. We have the orientation at -90, which is pointing down. Okay, that's -90 from a horizontal, so I'm facing the rod end down. And then this motor brake required. This is, since I'm in vertical, this doesn't affect the actuator. This affects whether or not you would put a motor brake when you go to pick out your motor itself. So it really is that simple. We click next. This takes us to the most important step in the sizing. This is the motion profile. I think we've done a really good job of narrowing it down and making it simple for you. We're walking through, out of my 300 millimeters of travel, if you follow this column, my displacement, I'm going to extend 300 millimeters, subtract 150, subtract another 150. My time slots are in here, so I'm doing 12 inches in 3/4 of a second, dwelling for a quarter. Okay, and you can see what I'm doing here. The payload attached is 12 kilograms going out, 20 coming back. So it gives you the ability to really narrow it down. I say dumb it down, narrow it down, make it easy on you. The axial thrust would be if you were inserting a part. In this application, we're not doing that. But all in all, this cycle time here is 4.5 seconds. We click next, and this is where all the computing in the background, this is the software kicking in. It's going to look at the actuators that'll work for you. In this case, this application, all 6 sizes are working just fine. We can actually hold the control button and compare a couple of different ones here. These are all the size 32, 40, and 50. Gives you the ability to compare thrust, the motor speeds that are going to be required to do this application. And usually when I'm sizing a pneumatic actuator, the weight is a big issue, right? So if you're going to size it based on weight, this would be in the bottom line. And of course, you get your charts too, and this comes up in the next step as well. So I'm going to go ahead and see how the size 32 looks for my motor controls. This is the summary page. This is the page that you would print off, show it to your motor guy. If you are the motor guy, all your info to size up that motor is on this size, step number 3. Okay. Don't get me wrong, the motion profile is very important too, but this is where you're going to have the motor requirements, the torque requirements, the speed requirements. And once you select a motor, you can actually insert the motor inertia here. Now, taking all that in consideration, the next big step is going on to the CAD configurator, right? We made it real simple. Right here on this sheet, you have a nice hyperlink. You click the hyperlink. It takes you to the CAD configurator. And this is not a warning message. This is just telling you, hey, we've already pre-populated with the information that you had from the data sheet. It filtered out here. If I want to add a front base mount, if I want to add a rear base mount, add switches to it, that sort of thing. But the most important thing on here, is going to be your motor code, right? And right now we've pre-populated it with the WXXX. I click the motor control. This is where I get to choose. Okay, maybe you're not at that point. You don't know what manufacturer you're going to choose. You're going to go with the WXXX for now. You can actually order it with a blank plate as well. But the list of manufacturers continues to grow. We'll look at, pretty common Allen Bradley, maybe a TL series. And then let's say you got to this point and you don't see your specific motor. I'm going to go ahead and choose this one for now, but if you scroll down, you get the ability to request to add motor. This sends an email to PhD, and you tell them what motor and shaft size you need and all that. I'm going to go ahead and say accept. You can notice the motor code now is a W0133. All right. The ability to preview a CAD. If I click the preview CAD button, it'd take about a minute or so to generate, and it would turn out something like this. This is where I get the ability to see online exactly what I drew up without actually downloading it or having it emailed to me. So you can zoom in. Oops, sorry guys. Going back to the CAD configurator, if I say get CAD now, I can always add it to my briefcase and continue to build other models. If I get CAD now, I want to show you the different formats available. This is where we have it emailed to you. You can, once you have your account in there, you can actually email it straight to somebody else, email it to yourself, forward it on, whatever is easiest. Change if it's extended or retracted. But the CAD formats, this is the part that we wanted to stress. These are the native CAD formats available for download. The native on the left, neutral files on the right, over 80 CAD formats available. This PDF data sheet, this is actually, you can choose 3 at a time. I can actually choose solid edge, PDF data sheet, and maybe a JPEG if I wanted to. Now everything grays out because I've chosen up to 3. But this PDF data sheet is the one I want to show you the most. Let's take a look at what that would look like if you were to receive one. On this on this PDF data sheet, you'll get your information on your local distributor in your area based on your zip code, right? All the information about the actuator. Notice the ECV is an ISO VDMA standard, so anywhere a pneumatic ISO would be size 32, 40, 50, you pull it off, put a electromechanical in its place. It's that simple. But as you go through, you got benefits and the delivery standards for the ECV. But the cool part about it is this is actually a CAD model of what that part number is at the top. So I can zoom in, I can see what it's all about. This is a great file to hang on to, throw it in your binder, email it off to a customer if you're an OEM, whatever makes the most sense. But it's really that simple.
Next up we have John. John, it's your turn to talk about some application flexibility examples.
All right, thank you, Paul. Good afternoon, ladies and gentlemen. I'd like to I'll just go over some ideas that we have with applications with some of our electromechanical products. First thing about applications is typical applications are usually going to be a retrofit of the mechanically coupled devices, things that have been in existence on equipment already that you have in-house. The other kind, and these are mechanically coupled, and I'm going to differentiate a little bit here in a moment. The other kind is the retrofit of an existing pneumatic or hydraulic point-to-point type application. Those are a little bit easier to do. And then the third style of application would be a totally new planned application entirely. The retrofit of a mechanically coupled device usually is involving some kind of modification of an OEM or an existing in-house equipment. Let's use an example of a molding machine, and some of the reasons that you might want to do that are you need a greater degree of motion control. Maybe the process has changed in your molding operation and you need some subtle variations in actuator velocity or force during a motion that previously was dictated by the shape of a cam or the length of a linkage piece. Those can be a little bit difficult to implement. Let's say in a packaging machine, you might have some equipment that was originally intended for one type or size of package, and now you're going to repurpose that to produce multiple sizes, different styles, and you demand some flexibility in actuator travel or possibly velocity. A third kind of machine might be an assembly machine. And as manufacturers' products change, the products that run across dedicated assembly machines, they might have some kinds of differences in mechanically coupled motions that present some problems that by incorporating electrically powered devices, you gain some flexibility, maybe allowing you to run different products across a line all with the flip of a switch there. The only problem is a retrofit of the mechanically coupled equipment it's not usually easy because you're interfacing motion controls with mechanical cams and linkages, and that could entail a high degree of sophistication or control change, and sometimes the payback might not be there, it just might not be justified. When it is justified, and when you can change out a mechanically driven device with an electromechanical, the gains in flexibility could give you a lot longer life than you might have had on previously dedicated machines. The second type of application should be something like the retrofit or enhancement of a pneumatic or hydraulic application. And an example of that might be looking at dispensing equipment. For instance, you might have a piece of equipment that dispenses an adhesive or a sealant, and that's being applied to your product as maybe a seal or a gasket. And if the original shape or pattern of that has changed and now you require some different changes in travel or velocity, that's a lot easier to do with an electromechanical device than it is with a pneumatic device. In food or beverage dispensing, perhaps the viscosity of the product is changed or the volume is changed, and different setups would be required. Well, with an electromechanical device, replacing a pneumatic or hydraulic one, you could change things with the flip of a switch. Might also have some labeling or marking, and as products change across there, perhaps there's some variations in force that are required for different labeling for different products. Again, replacing a pneumatic device with an electromechanical here is a little bit easier than with something that's a cam or linkage driven. Let's consider a die cutting or a routing application. That's something there, as you can see in this example, there might be some type of linear or circular interpolation required during this operation. Very, very difficult to do with pneumatic or hydraulic, but if we retrofit that with an electromechanic, that's pretty easy to accomplish with today's motion controls. And the retrofit of point-to-point pneumatic and hydraulic actuators is a lot of times accomplished with just some mechanical mounting changes for the devices and then some PLC programming changes and the addition of motion controls. Let's take an example here where we've got a drilling and pin insertion station, and we're going to look at this example where we have a two-position pneumatic horizontal slide, a two-position pneumatic vertical slide, another two-position pneumatic vertical slide operating these drill heads, and then possibly a three-position cylinder that's used to advance the product. Okay, first the holes are drilled in one position, and then the pins are picked and placed by this pneumatic vertical and pneumatic horizontal slide. And then finally, the three-position slide would be used to advance the product out of the field of motion or the field of operation there. Well, what if the customer's or the user's application's changed, and now he has to put in a couple of sets of holes, and he's putting in a couple different sets of dowel pins at different heights? Let's take a look at an example like that. And here we've replaced a two-position horizontal slide with an electromechanical. We've replaced the two-position vertical with electromechanical. We can drill to different depths with this electromechanical. We can pick up from a couple different positions and a couple of different heights. And furthermore, we can advance the product through these various stages at several different positions. In this first position, we're drilling a pair of holes, and we're picking up a pair of dowel pins to insert into those holes. In this next stage, we're drilling a second set of holes, and then we advance that product and insert a pair of dowel pins into the first set of holes. We can go back to a second pickup station that has different heights, and then insert those pins into a set of holes, and then advance the product out of the field of the operation. All of this done fairly easily with various electromechanical devices that have the ability to achieve different positions. If something changed perhaps on this product of the users, where those positions of the pins was going to vary on the next run, flip of a switch, and this slide can change that advancing to different positions to help accomplish that. A lot of these applications that are being seen these days are in assembly and die cutting, all of these operations that you see listed here. We also have a lot of operations of part loading, sorting, clamping, just a wide variety of different types of applications that are enhanced by the use of electromechanical devices. And the key here is the flexibility of position, force, velocity. All of those things really make these new applications very attractive for electromechanical devices. Some of the things that we see here at PhD with our products are applications in food and beverage industry, for example, stacking and weighing operations, and the electromechanical makes that very attractive for stacking product at various heights. Also flexible packaging, different size products being packaged at different times. Again, with the flip of a switch, things are reprogrammed and ready for a different type of product to be packaged. Other industries might include electronics and semiconductors, where we're picking and placing various size components, putting different products on different locations on circuit boards, things of that matter, and also doing some marking and possibly part identification. Some of the applications in automotive industry might include flexible assembly machines. Again, controlling the motion of velocity, controlling the position, controlling the force with a great degree of flexibility. Possibly mounting cameras on the end of tooling for inspection. In the life science industry, moving test specimens through procedures, automating labs, moving around test tubes, petri dishes, again, moving cameras for sample identification, things of that nature to various positions are good examples of applications for electromechanical devices and their ability to position. So really, in summary, new applications for electrically driven automation actuators can offer a lot of flexibility for position, velocity, force, along with some of the energy cost reductions, and could ultimately deliver some of the best return on investment. What we'd like to know is, has your company used electrically driven actuators to replace a mechanically driven cam or linkage device, or a pneumatically or hydraulically driven device, or both? This really reflects a lot of what we would expect to see, that pneumatically or hydraulically driven devices are a lot easier to make changes on existing equipment than those that are mechanically driven, cam or linkage type devices, just because of the sophistication of the cam or linkage. Got another question we'd like to pose to you real quickly. We'd like to know if your company has any kind of initiative to use electrically driven actuators where possible instead of mechanical. We could open that poll here, and you only get to select one this time. What we are seeing are a lot of industries are making a move toward electrically driven actuators. Some are even, depending on the type of industry, some are even considering all electric facilities, an all electric factory where they don't even have compressed air. Now, that's not something that we've seen come to total fruition yet, but we've heard talk of that sort of factory. Let's see, looks like most of our vote is in here that's going to come in, so let's go ahead and share that. So, it does appear that, yes, we do have some initiatives out there where electrically driven actuators are certainly overtaking pneumatics. That's interesting information for us here at PhD. It's something that we consider as we develop products, and I'm sure it's something that you are thinking of as users of automation. So thank you for participating in the poll. And at this time, I'm going to turn things back over to Paul.
Well, thank you, John, and very interesting polls, too. I got a lot out of those. Our fourth presenter, Ryan, will now discuss some specialty electrical products. Ryan, what do you have for us?
All right, thanks, Paul. Throughout this presentation, we've discussed standard off-the-shelf items. But what happens when you're unable to find that actuator for your specific application? PhD has a group that we call PhD Unlimited, where we specialize in unique actuators that fit specific applications or your specific environmental needs. We have a very good track history of quick turnarounds and providing very in-depth solutions for these projects. A few of the specific industries and environments that we see on a regular occurrence are listed below, and I'm going to go into a little detail on each one of those. As you see, the food industry requires actuators and machines to have specific materials and/or plating such as stainless steel, polymers, and other industry-specific seals and lubrications. We see applications requiring electrical actuators to control operations in both the food processing and packaging sides of the plants. Along with the food industry, the medical industry is seeing applications with very similar materials and lubrications. We have been involved in all aspects of the medical industry, from the test equipment to the medical supplies and to the prescription filling even. Along with these two industries, the semiconductor industry also lends itself very well to unique actuators. This can vary from very small precision actuators to very high-speed multi-axis applications. These are just a few of the industries that serve themselves very well for unique actuators. And within each of these industries, we see packaging equipment, wash-down applications, and some very specialized equipment built for those industries. The packaging equipment is evolving into multi-product lines where electrical actuators work very well due to their flexibility and multiple programs that can be run through their motion controllers. Wash-down applications can be one of the harshest environments in industry and often require special materials to handle the chemicals used. Special precautions must also be taken in sealing these electric actuators and motors from the solutions and chemicals being used. I'm going to open up a poll question here based on the applications we're talking about and the environments to see what your company's requirements are when using unique applications. What's the most common material you might use? Whether it be aluminum, stainless steel, a certain type of polymer, or something else that's not listed here. Well, it looks like we've got a kind of a balance between aluminum and stainless steel being the most common. And when we're talking about the industries such as food and medical, stainless steel is going to be the prevalent use of material there. Right, using that information from the poll and seeing that aluminum, stainless steel, and polymers are some of our common materials being used, we're going to talk about some of the actuators and materials in detail and go into detail on each one of these actuators. And these are just a small portion of what we see out in the industry. As you can see on the screen, we have three images of grippers. The one that's highlighted here is a small 3-jaw gripper. This unit here has 3 jaws that be used for picking up cylindrical parts. It's got a 90-degree motor inline drive here. Basically, that can keep your center of gravity very close to the gripper, so that if you mount this to the end of a robot or the end of a pick-and-place application, you're going to keep your center of gravity very close and be able to have higher speeds and higher moment capacities. This other gripper here, shown in the middle of the page, is an all-polymer unit. This unit is very, very light, So it can be used as an end effector on a robot to keep the payload low, to keep your cycle speeds high. And you also can eliminate all the air lines going to the end of the robot if you do not have those wired into your system already. The last gripper that we have here is a full stainless steel unit. This unit here is a 2-jaw parallel gripper. It can also be used as an end effector for a robot or in a pick and place. The difference between this one is you've got stainless steel material rather than polymers, which suits itself better for higher moment capacity, higher grip forces, and also, as you notice, with the no extrusion, no grooves in here, suits itself very well for wash down and food applications. Along with the grippers, we also have a cylinder pictured up here. This unit here can be used, was developed with a low-cost lead screw-driven actuator used on agriculture equipment. Provisions were taken on this unit to seal the unit from the elements and protect it from, and all the components from corrosion. Along with cylinders, we can also do slides. This unit up here in the upper left is a base or gantry type slide. This unit was developed for the food industry and engineered to be an IP67 wash down compliant device. The design and materials were chosen based on the customer's applications and applied for optimal performance. And lastly on this page, the one being highlighted here, this here is a variable pick head. We designed this unit to have multiple heads that when actuated will pick up a part and spread it to the place the customer's given configuration of the part. These type of actuators get used in packaging and unpackaging applications commonly to pick and place into boxes or onto conveyors. If we go on to the last poll question here, basically we want to open this up and we want to take a look at seeing what type of electrical actuators do you most commonly use. We've got selection for single axes, where it be a lot of the components we showed you today, which would be cylinders, slides, grippers, rotaries, Cartesian systems, which would be an XYZ table or a combination of single axes, scale robots, or articulated 5 or 6 axis robots, or if there might be something other that you're using. We'll leave this open for a few more seconds, see what type of components that are most commonly used out there. So as we can see here, it looks like a lot of the applications out there in the industry are using the single axis components. So we can take and look at all the components we were looking at today and use those in any combination you might have to put those into your applications, and as Cale mentioned earlier in the presentation, to see which one of these components might work best in your application, whether it be pneumatic or electromechanical. So I think that was last one here, and just in summary, as you can see, there are very many variations to the standard electrical actuator market. But keep in mind, when your application calls for specifications outside the normal operating parameters, there are still other opportunities here, and at PhD, we'd love to help you in the future. I'll turn it back over to Paul now, and I think we can go over some questions and answers at this time.
Sure. Thank you so much, Ryan, and great information, all of you gentlemen. Thank you all so very much. All right, we will now use the remaining time for questions. We do have some that have been coming in, but it is not too late to send in your question. Just simply use that dialog box on your GoToWebinar screen, and we'll try and answer as many as we can here. All right, gentlemen, and I will just, unless specifically oriented toward one of you, I'll just throw these questions out to all four, and you can answer as you see fit. The first one I've got, how much change is involved in retrofitting a machine control system from pneumatic actuators to electric actuators?
Well, I'll take that one.
Okay.
Paul, this is John. That really depends entirely on, I guess, first on the number of axes to be converted, and also whether the existing control system supports the kinds of cards and motor drivers, things like that, to control the converted axes. In general, the addition of 1 or 2 axes of control is not extremely complicated. if the existing control system has room for expansion and supports motion control components, then maybe it's just adding a card or two to be able to do that. Another option then might be the addition of an independent controller for the electrical axes, and then some level of communication or handshaking between the original host control and the new controller. So normally that's in a pick and place type application, or an application where just some additional flexibility is needed in positioning. That's typically not too difficult.
Okay. Someone else asks, can I get high speed and high force out of electrically driven actuators?
Cale, that's kind of up your alley, but I guess my first blush would be that, yeah, however, there's normally a trade-off between force and velocity. What's your thoughts on that?
Well, it really kind of comes down to how high a force or how high a speed do you need. Depending on what lead of screw you've got in your electromechanical actuator and how fast you spin that, I mean, you can keep sizing your actuators up larger and larger and larger, and you can typically get higher leads and larger actuators, such that you would result in an actuator that was properly sized for your application that was capable of both the thrust and the speed that you required. It's just a matter of knowing the application requirements and then sizing the appropriate actuator. But as far as a trade-off goes, it's kind of one or the other as far as picking that screw lead.
Fair enough. All right. Can linear interpolation of two axes be accomplished with stepper motors?
Yes, there are controllers out there that do control stepper motors that can accomplish linear interpolation. However, the more sophisticated systems, and therefore a little bit more expensive systems, are going to be servo systems. The stepper systems normally are going to be running open loop, even though they may be controlling the position feedback or looking at position feedback while they're moving. Ultimately, it's like a correction factor rather than compensating on the fly. There are possibly some very sophisticated systems that can do that, but normally there's going to be a little bit more expensive. And most of the interpolation, whether it's linear or circular through two or more axes, it's usually best controlled with a true servo system.
All right. Another question coming in. How do you justify or quantify the return on investment for the much higher cost of electrical actuators than pneumatic cylinders? Are there any calculation matrices that you can suggest that they could use to calculate the return on investment?
Well, in the past, what PhD's done is we've made software such that you can calculate the lowest cost of ownership for our pneumatic devices. That way you can go head to head and figure out, well, what is the best solution for your application. We've got quite a few years under our belts doing that. As far as the electromechanical versus pneumatic goes, we are in the process of developing a same kind of piece of software that will allow our customers and our distributors to go in and take a look at both a pneumatic and electromechanical options to an application and size them up and figure out which is the right solution or the right path for them to take. So as far as a product from PhD, that is in development for us, and a tool that we would like to add to our toolbox among all the many other tools that we have out there for our customers and our distributors to use.
Fair enough. Someone asked, why not compare pneumatics against electromechanical solenoids, and wouldn't this be more on the same level?
Well, the electromechanical solenoids that I'm aware of are very small. They have low thrusts, very short strokes, and low duty cycles. They will overheat over time. The actuators that we're speaking about, or at least the ones that we have the most experience with, are large actuators. We're talking strokes up to a meter in length, and some very large thrusts. So, you know, it's kind of a different scale of product is what we're talking about here. So that's why I didn't really address solenoids as a solution in the scope of this presentation.
Okay, fair enough. We are running out of time here. We've gone over the promised hour, but so that's all the time we have for questions right now. But actually, the very nice people at PhD have said that they would be more than happy to answer further questions. So you can continue to, you know, enter in any questions that come to mind into your GoToWebinar, and they promise that they will follow up with each and every one of you afterwards. Besides that, if you think of something later on today or tomorrow, you are more than welcome to send me an email. My email is pheney, Pheney, at wtwhmedia.com, and I will be most happy to forward your questions on to these four gentlemen. Well, thank you, everyone, for attending today's webinar. I think this was a great webinar, again, sponsored by Design World and PhD. And thanks to Cale, Carrie, John, and Ryan for speaking today. Now, as I mentioned earlier, this presentation will be emailed to everyone in the coming days, and the presentation will also be available in the coming days at www.designworldonline.com. Thanks again for coming, and have a great rest of your day. Goodbye.